Hi, I'm Chuck Deeter here at the Headwaters Science Center to bring you a little bite of science. And my finger's on fire! Okay, my finger's not really on fire. You can tell because I'd be screaming and trying to put it out if it were really on fire. But, well, what's happening then? It's not a trick, it's not a video editing trick, it's a real flame, real finger, and I can feel some heat from it, but it's not burning my finger yet. So what was that? How did that happen? Guarantee it really was a real flame. Now that is something that I ordinarily do in our combustion demonstration. Combustion, C-O-M-B-U-S-T-I-O-N, 10-letter word that means fire. We like to use demonstrations here at the Headwaters Science Center to introduce, illustrate, kind of get across some basic scientific ideas. And that's one of the things we do in our combustion demonstration. We do a lot of other things too. You get that figured out? How did that happen? How did I make that work without burning my finger? Here's something else we do. This is a pretty common one. Now in this little beaker I'm going to put, well, can you read it? It says, let's get this so I can see it. Yeah. Isopropyl alcohol. You got that? Isopropyl alcohol. And it's not a trick. I don't have water in here or something. It's a real flammable liquid. It's real alcohol. And in a video, of course, I can't prove that I'm not tricking you somehow. But can you guess what I'm going to do? Recognize Abe Lincoln? It's a $5 bill. I'm going to put this ordinary paper, U.S. currency, hope that didn't get me in trouble, bill into this beaker and soak it good in a flammable liquid. So how many of you out there are thinking this is going to cost me $5? Now how many of you are thinking this is going to cost me $5? So flammable liquid. Now paper burns at about, well, the usual temperature you see listed in reference sources is 451 degrees Fahrenheit. That's when paper will start burning. Alcohol, well, it depends on what kind of alcohol, but it'll burn pretty much with a temperature of well over 1,000 degrees. So I'm going to have a temperature of well over 1,000 degrees right next to this paper $5 bill, and let's see what happens. Oh my gosh! I'm losing my money! I'm losing my $5! Didn't lose any money. So what happened there? Why didn't the paper burn? And why didn't my finger burn? Well, science. I was using science to control what was happening. Just some basic scientific ideas. So you might ask, well, what's so scientific about combustion, about burning? You see things burning all the time. Well, it is pretty scientific when you really get down to it. For one thing, combustion is a chemical reaction. A chemical reaction is what happens when two or more substances come into contact with each other, and they change. Sometimes atoms combine with atoms, and molecules break apart, and their pieces are atoms and what you call, well, anyway, their pieces recombine and make different molecules, and you end up with different substances than you started with. In the case of combustion, what you're doing is you're combining oxygen, which usually comes from the air, sometimes from another source, with, well, there's a whole class of substances, and we kind of generally clump them into the category of fuels. It's a fuel. Lots of different kinds of fuel, paper, wood, grass, gasoline, all kinds of different kinds of fuels. But what they all have in common is they will combine with oxygen very rapidly. Now, some chemical reactions happen spontaneously. If you have, say, a little bit of baking soda and you pour some vinegar on it, you'll see a reaction. It just happens because the two of those substances come into contact with each other. Some chemical reactions require a lot of energy to put into them to keep them going, to make them happen constantly. And the ones that require energy input are called endothermic reactions. Now, some chemical reactions produce their own energy and give off energy. And obviously that's what combustion is. It gives off heat and light, and it's a self-sustaining chemical reaction. Now, in the case, so those are called exothermic reactions. So there's a couple of good scientific words: endothermic, exothermic reactions. And now in the case of combustion, it takes a little something to get them started. You have to kickstart them with some energy to get them going, but once they get going, it produces enough energy to keep itself going until one of those things runs out. See, that the three things that you need for a combustion reaction are heat to get it started, and you need oxygen, of course, and a fuel. Oxygen, fuel, and heat, the three things you need for combustion. And if you can control those things, you can kind of control the combustion and what it does. In the case of the finger, I wasn't really burning my finger, of course. What I had was, if you can see this up close, try to get it close to the camera. You see, that's a little glob of petroleum jelly on my finger with a piece of candle wick stuck in it. And what was burning, of course, was the petroleum jelly, but not the petroleum jelly in the gel form. What happened was, well, the petroleum jelly kind of soaked into the candle wick. And when I applied some flame to it and got it hot enough, the petroleum jelly in the candle wick liquefied, but it didn't stop there. It went from liquid to gas, and the gas is what ignited. The gas is what started burning, and what you were seeing was burning gaseous petroleum jelly. And it kept going because it provided enough heat to liquefy the petroleum jelly just below the flame. Now that's soaked into the wick, and a process called capillary action drew it up the candle wick to the base of the flame. That's another good scientific process you might want to look up. Basic scientific idea: capillary action. When it got to the base of the flame, it got hot enough to vaporize, and the vaporized petroleum jelly burned and provided heat to get more of the petroleum jelly below it liquefied and going up the candle wick by capillary action, and the whole thing kept going and going and going. And also another good, helpful scientific process called convection, convection, which you might want to look up, made sure that the heat and the products of the combustion were going upward away from my finger. And as long as that whole complex of things kept going, I could have that candle wick on my finger burning and well, actually using my finger for a candle holder, because that's essentially what that is. It's a candle. Well, that's what happens with a candle. Here's my candle. So there's the wick, and it's got some candle wax soaked into the wick. So if I apply enough heat to this to liquefy the candle wax and to start the liquefied wax vaporizing, you get a nice candle flame. So what's happening, of course, is the heat is liquefying the candle wax. It's going from a solid to a liquid. Basic scientific idea. It's soaking into the candle wick, going upward through capillary action, vaporizing at the base of the flame, and producing heat and light. Light's usually what you want from a candle. And the whole process makes this, the convection process makes this whole nice candle flame going upward, and you get the combustion you want, not the combustion you don't want. So, well, now what happened with the $5 bill is I cheated a little bit. I did trick you a bit. If you look carefully at this, I'm going to bring it closer, you can see it says 70% isopropyl alcohol. So 30% of this is water. And when alcohol soaked into the $5 bill, it also had some water in it. So there's water in that $5 bill. Now, when it started burning, the temperature was plenty high enough to get that the $5 bill burning, but in order to get it to combust, you would have had to evaporate all that water, because water has an amazing capacity to absorb energy without changing its temperature. It takes a lot to get water to evaporate. There's a whole lot of energy out in the atmosphere that makes that happen all the time. But anyway, the idea is that before the water in the $5 bill evaporated, the alcohol was all burned off. So I knew that if I soaked this in 70% isopropyl alcohol and set fire to it, I wouldn't lose my money, because I was controlling the heat, the fuel, and the oxygen in a way that that worked. So that's enough for a little bite of science. Think about that. You might not have done much with science, or might have had a great interest in science, but every time you light the candles on birthday cake, anytime you strike a match or get the charcoal going, get the grill going out and back, you're using the science of chemistry. Anytime you even light a little stub of a candle. Look at that. Science! Well, that's about enough for a little bite of science for right now. Food for thought.